Okay, I want to talk to you a little bit about malware and malware samples and how viruses and trojans and worms work. We can get into a little more detail on this in the slides coming up. But just keep in mind one thing is if I have malware can be, it's usually in the form of a file, right? So if I have a file and it's malware, and I'll kind of draw my skull and bones. That's my version of skull and bones. Don't laugh at my drawing, but just pretend it's a bad file. It's a malicious file. Well, what makes a file malicious? How do we know that it's a malicious file? Well, normally we had antivirus engines, right? So we had like AV engines, antivirus engines, and they kind of determined, hey, this file is a bad file. So how did that antivirus engine actually determine if that file was a bad file? Well, what we did was we actually took a fingerprint of this file. So a lot of times antivirus engines, they cannot ingest the entire file. They have to actually ingest a fingerprint of that file. So what we do is we actually run this entire file through a hashing algorithm. There's multiple hashing algorithms out there, but the ones that are most commonly used is called MD5 or SHA. And there's multiple SHA algorithms out there. There's like SHA-1, SHA-256, SHA-512. I would say SHA-256 is the most commonly used one right now. And these are just worm checksums. So this is basically an algorithm to determine what the fingerprint of a file is. Now, just real fast, how does SHA algorithms work? Well, basically what an algorithm does is it basically takes something that's variable size, it goes for a mathematical algorithm, and what comes out on the other end is something that's a fixed size hexadecimal number. That's the fingerprint. So think of it as almost like a funnel. Like, I guess that's kind of how a funnel would look. And in the funnel, we can feed like lots of different things. We can we can drop files in this funnel. We can drop movies in this funnel. We can drop entire hard drives in this funnel. From a computer's perspective, it doesn't matter. It's all zeros and ones. It's all data. The funnel is actually going to go ahead and put a algorithm on that. Let's say SHA-256. And what comes out is that unique piece of data, that unique combination of data is going to form some sort of algorithm, some sort of fingerprint. The fingerprint is going to be a hexadecimal number. It's going to be a pretty long number, but it's going to spit out this fingerprint. Now, this fingerprint is unique to that data, and that's important to know. So if I take a file, let's say if I take a file and in the file I have the word hello, or let's just say hi, and that's all I have, and I put it for the SHA algorithm, and I get a fingerprint back. If you take that same file and you put the word hi in it, and you put it through the SHA algorithm, you're going to get the exact same fingerprint back, the exact same output back. So it doesn't matter like who makes that file. If I make it, if you make it, if someone across the world makes it, we're always going to get the same fingerprint back because the data is exactly the same. That's the fingerprint. It's just like if I take my fingerprint in California and I take my fingerprint in Texas and I take my fingerprint in Singapore, my fingerprint is always going to get to be the same because it's going to belong to me. This fingerprint belongs to the data of a text file that says hi. Now, if we ever have a file, if we have another file, hello, it should produce a different fingerprint. But for some reason, if we ever get the same fingerprint, for some reason, if two unique pieces of data produce the exact same fingerprint, that's an error. That should never ever happen. Just imagine if two people in the world had the same fingerprint, you could have problems, right? One person may be committing a crime, the other may not, right? You could have a problem. That's an error in the hashing algorithm. It should never happen. But it can potentially happen. Why can it happen? Well, we have unlimited amounts of data. So remember, there's an unlimited amount of data. So every time I put data for a hashing algorithm, there is a possibility that maybe I could have some sort of duplicate happen. If that ever happens, what do? We just go to a more complex hashing algorithm. Back in the past, we used to have an algorithm called CRC. We've started finding a lot of collisions or a lot of errors or duplicates. These duplicates are also a lot of times called collisions. That's what we call them. So we had a lot of collisions in CRC, so they actually decided to make the algorithm a lot bigger. So basically, it produced a much bigger hash, and it was called CRC32. Eventually, we started seeing collisions in CRC32, so we went to an algorithm called MD5, and we started seeing collisions happen on MD5, so we went to a more complicated hashing algorithm. And today, what a lot of people use is SHA-256, and SHA-256 is a much larger algorithm. It has a lot more hexadecimal numbers, which means there's a lot more combinations, which means the likelihood of collisions is very low. As of today, we have no known collisions in SHA-256. We do have some known collisions in MD5, but they're very rare, and because they're a very small amount, MD5 is still used. CRC and CRC32 has a lot of known collisions, so they're pretty much not used today. Now, why do I bring this up? First of all, I bring this up because this is one of the most common ways to categorize malware. When someone actually sends you malware and says like, okay, I'm sending you a file, bad file, and I know I'm hard to see here, but just keep up with me. So if I have bad file and it sends this to you, some other malware author is going to say, you know what? That's a good piece of malware. I want to use that somewhere else, but I can't call it bad file. If I call it bad file, everyone's going to know that's a malicious piece of software. So I'm going to rename this good file. Hey, that'll fool people, right? If I call it good file. But good file is going to actually have the same hash because the contents inside good, the actual malware program, the malicious program, is going to be the same that was in good file. So we just changed the name. We didn't actually change the content or the data. So the data is going to produce the same hash. Now, why malware authors and security researchers refer to the hash of a file is because the names can change all the time, but we're worried about the data inside those files, the data of the malware. We're wondering what makes bad, bad. I always say that, what makes malicious, malicious. Well, it's that data combination, and that data combination can be fingerprinted. All right, so I'm going to throw one more wrench into this whole problem is malware authors started figuring that security researchers were looking at the fingerprint of the file. And they said, you know what, if I open up this malware, if I actually open up the data and I modify this data, say if the data has something like A, B, C, what about if I had a D in the data? What about if I just open up this with a hex editor and I add a period? What about if I add like a dash? Guess what? The program still works perfectly fine, but now the fingerprint is going to be completely different. Why is the fingerprint going to be different? Because the data we're fingerprinting is different. It has some additions based on it. So they were saying, hey, you know what? I can change how researchers look at this file. And that's how traditional AV actually caught malicious files, is it was looking at the fingerprint. But as soon as malware authors started changing that fingerprint, AV, signature-based AV, doesn't work anymore. Signature-based antivirus doesn't work anymore. And that's why it's so easy for malware authors to take an existing piece of malware and just change it just a little bit and still have it work perfectly and bypass all the security measures you have on your PC. Now, it gets even more complicated than that, and of course, it's a cat and mouse game, which we're going to talk about in the next couple of lessons. But this cat and mouse game basically allows security researchers to try and catch up with the new techniques with malware authors, and malware authors trying to outthink and outsmart the security researchers. Okay, so I hope you enjoyed my little session on my introduction to malware. I want to get into some very specifics now and talk about the malware threat landscape. So let's talk about a few different things on what happens today. The reality is it's a very reactive world today. A lot of times, as security analysts, we'll come across viruses, Trojans, malware all the time. And we're looking for security products, we're looking for security programs and techniques to fight those when we run across that. And unfortunately, it's still kind of like the norm. Obviously, things like AI, artificial intelligence, machine learning, behavioral-based, anomaly-based systems are trying to combat that, and it's starting to finally take a hold. We're starting to make the shift where we're not just reactive around network threats anymore, but but in the past we've definitely been 100% reactive, and now we're moving more towards proactive and predictive behavior. So that's the solution on how to get past today's very volumetric type of attacks, and a lot of variety in our attacks as well. So I want to talk about normally the virus life cycle. Usually, and this is just an example, when a virus is released into the wild, within a couple of minutes, sometimes less than that, the virus starts to mutate. Just like we have mutations in the real world, we're always scared of, right? We have our, normal variants, and then we have our mutations. Our mutations, a lot of times, will basically bypass a lot of security products, just like in the real world, how mutagen viruses can bypass a lot of techniques. What starts happening is the mutants start mutating, they start changing the viruses. Now, unlike organic viruses, this is not occurring in biology. A lot of times people will come across these viruses and they're like, oh, I can make this better, I can change this, I can add something to this. Now, it's true, like some viruses may have polymorphic code, so it may mutate or update itself in some ways, but we're not normally talking about that. We're talking about actual malicious actors manually looking at those techniques and mutating those techniques. And of course, that's a vicious life cycle that occurs over and over again, and until you have many different mutants and many different techniques. What happens is usually your security vendor, within an hour or within like 2 hours, usually they're issuing a signature update. But the signature update they're issuing was usually based on the original virus or the first few mutants. It's possible, even likely, like I said, this is not a biological attack, so it could be very likely the code base is close enough or similar enough where the antivirus software will catch the modified viruses, the modified mutants. But it's also likely that it may not, because it's just looking for, especially depending on how that antivirus is trying to catch it. If it's string-based analysis, absolutely not. If it's hash-based analysis, absolutely not. But if it's using behaviors or something, then maybe it may be able to catch even the second generation and third generation of viruses. You can see how quickly this occurs. In my timeline, I have like within 30 seconds sometimes mutagens start occurring, and that is, I know that sounds pretty extreme, but it's not that far, from the truth. Depending on the of course, the volume and the vectors the virus is taking, the distribution channels, and really how popular it is, and what's going on with that. So let's talk about how malware initially worked. It used to use a very simple checksum. Basically, you had a malware file. That malware file was hashed, and antivirus looked for that specific hash. So you match the hash, you basically had a malware. So antivirus was only searching for the hash of the file, the worm checksum of the file. The reason it was doing that was because it's easier to do that than check the whole file. What attackers started realizing is, if I change one code or character or add a space, a period or something in my hash, the program runs absolutely fine, but now it will be missed by antivirus agents. That is a discussion for our next lesson, so I will see you in our next lesson. Thanks.